So here was our other example. So retinoic acid, or vitamin A, is another type of signaling molecule, and we want to look at, let's say we want to measure the interaction of retinoic acid with its receptor, and we've isolated this from a whole cell lysate. So we had some cells, and we could have, maybe we chemically dissociated their membranes or busted them open, or mechanically just pipette them up and down until you break them apart really aggressively. I used to do that. It's called trituration, but that's just a fancy word for pipette up and down over and over to mechanically break apart stuff. So what we have here is then I have a solution of my actual retinoic acid receptor that I'm interested in, but then I don't know how much protein receptor I'm starting with. There's a bunch of other proteins and other things in there. I then also have radioactively labeled retinoic acid, so I have my tritium tagged vitamin A in this case. I mix these two things together just like before, and I sort of wait for binding to happen. And then this is where I said if you put in some activated charcoal pellets, this is another possible separation technique. In this case, they will take up unbound retinoic acid. And so then again, you can centrifuge this pellet of charcoal pellets with a bunch of the unbound stuff, and then you'll be left with your sort of receptors that are bound, but then also you'll have some other binding. And so we kind of said, you know, oh, ideally, you have binding that's only to the receptor of interest. But real life, you'll also get binding to proteins that you don't want in some minimal amount. It won't be strong because it doesn't have a really good affinity for this other stuff. You'll also get some attachment to like the sides of the test tube. And so, you know, your measurement will be imperfect. So what you want to do is sort of try to subtract out all of this background radioactive like signal that you would get, okay? So that you can just have the part that's actually bound of interest. So there's a couple curves going on here. The red curve, so here we have our tritiated retinoic acid in nanomolar, okay? So again, you have to do a bunch of different concentrations to set up your curve. And then this is the amount that is bound. So we have observed binding. Okay, this was like from your textbook. This is the complex concentration here, as opposed to fractional saturation. But you can get the 50% point or the 100% saturation point. Okay, the red line is the observed binding. So this is the full, complete signal you get off of your instrument, right? And that radioactive signal contains both the stuff that's actually bound, the stuff that's on the test tube, the stuff that's bound where you don't want it to other proteins that are not of interest. And what you'll see is that it actually shouldn't really be saturating ever, kind of. It just keeps going. As you raise the concentration, more and more of it can continue to attach to other stuff. Eventually, you could get it to attach to a bunch of proteins it doesn't want to if you just kept raising it and raising it, okay? So then you also need to get rid of all your background binding. And so what you want to do with the background curve, saturate the receptor that's specific. So saturate the retinoic acid receptor with a really, really high concentration of unlabeled ligand. So put your untagged retinoic acid in at a high concentration, usually 100 times what you expect to need. Make sure you saturate all the retinoic acid binding sites first. And because those things are more attracted, there's this stronger interaction between these two, those will get filled up first before the other stuff. Then add the radioactive ligand, and the only thing that the radioactive ligand will have left to bind to is nonspecific proteins and the walls of the test tube. And then, so any binding of labeled ligand is now only due to the other proteins and the other stuff you don't care about. Take this signal, subtract it from your binding, this is your total observed signal, this is your background signal, and what you'll have is a corrected binding signal, which eventually should saturate the way you expect it to. Okay? And so the blue curve is the one that's sort of real, and this is the one you want to get your KD off of, right? You'll be able to find a saturation point. You'll be able to find a half saturation point. Does that make sense for how to take out background? Okay. And again, a plateau in your isotherm is sort of this hallmark of specificity. It's a hallmark of saturable binding. If you don't have it, something else is probably going on. Okay. So how do you know that you aren't getting nonspecific binding of your untagged RA? In sort of this, in the background subtraction case, like when I put in my untagged stuff, I mean, some of it's going on to these other things I'm not interested in. You know, and then the issue becomes, these are some good questions that people came up with in past semesters. Are you doing enough subtraction, or are you doing too much subtraction? And that's totally valid. We expect the affinity for nonspecific proteins and the plastic of the tubes to be really low relative to the specific protein, right? So we kind of talked about when you have high affinity and you have this really low KD, then you need very little concentration to actually start saturating the receptors of interest. You're going to attach to all those things first before you attach to any of the nonspecific stuff. It doesn't want to bind that much. It's not that favorable. So if you use about 100 molar excess of your ligand, you can expect about 99% of the receptors to get bound. I haven't drawn a universal binding curve for you, but I will in a second, and then it might make more sense. Another option would be protein purification of your whole lysate before you conduct your binding assay, right? So you have your whole cell lysate, you can sonicate it or triturate it. You can use some sort of enzymatic lysis. You could freeze and thaw your cells a whole bunch of times till they bust open and again, get your proteins out. And then you can purify them. You'll separate the proteins based on some sort of property of the RA protein that you're interested in. So it could be based on charge, it could be based on hydrophobic interactions, it could be based on size, use some sort of filtration or chromatography technique, whatever it might be. Okay. So here is the first example problem. Here is an actual scattered plot for retinoic acid binding to its receptor. Find the dissociation constant using Scatcherd equation. So take a minute and do that. This is another one where, again, if you're given a plot, and you're obviously here, the first thing you need to do is find a slope, which is change in y over change in x. Pick easy numbers to use. Like, there are zeros there. Why wouldn't you use them? People will pick just the most obscure points and make it complicated for themselves. All right, who got a KD? And what did you get? 0.2 what? KD has units now. Molar? Nanomolar. Okay? So remember, we're interested, to find KD, we're interested in looking at the slope, which from our Scatcherd equation is given by -1 over KD. So we have our change in y. We're going from 0.3 to 0. Over our change in x, we're going from 0 to 0.0. This is unitless, okay? This is a ratio of concentrations. Our bound concentration now is in nanomolar, okay? 0 minus 0.06 nanomolar gives us a -5, but we're interested in -1 over that, so it is going to be 0.2. But also to make sure things make sense, okay? So now it's positive, 0.2, and we're in nanomolar, and molar units make sense for KD. You know, if ever, follow your units if ever you're unsure. And then remember that knowing KD, you could also calculate the receptor concentration you started with. So how do you do that in this case then? I don't think I have the answer pop up, but your intercept, your y-intercept is given by the total protein concentration divided by KD.